Now we move on to the more traditional variable selection methods, when we start with what we can call random variable selection, or methods that have a large random element to them, in that they randomly choose variables to test. Genetic algorithms is a good example of that, and we will try the genetic algorithm on the beer data. The genetic algorithm is based on what is often called survival of the fittest, inspired by Darwinism. But survival of the fittest here means that good models have a higher chance of influencing the result. We have a data set and we want to make a calibration model. Now from the data set we can generate different models by using different variables. And each such model using a specific set of variables is called an individual. For example, one calibration model could be based on variable 1, 3, 14 and 27. And with that model we could get a certain quality as defined by the prediction error. For example, a cross-validation or test set validation-based prediction error. So every model is defined by the variables and the quality of the model. We generate a number of different models, and then we find new models based on the results in such a way that the good models, those that have a low error, have a higher chance of influencing the result. The terminology used is that we start out with a population, for example 100 different individuals, and an individual means a model with a given set of variables. We have genes, and the genes define what variables are used. So it's simply a dummy vector with as many elements as we have variables, as shown in the figure below. If we have a 1 in the gene, that means the variable is included, and if we have a 0, then the variable is not included. So we start out with the population, for example, of randomly chosen genes, and we evaluate all the different models. Then, with these results, we generate a new generation, and we do that in such a way that the good models have a higher chance of getting into the new generation than the old one. Every child is made by taking 2 models randomly, but focusing on the good ones, and then mixing the genes. And then we continue with that until there's little change in the result. And from that we get potentially good variables. So as you can see, there is a large random aspect in this, in that we choose genes randomly initially, but we focus our results by allowing the good models to continue more often than the bad models. This is very useful, especially in situations where we have difficulties with finding a model. So maybe when we build a model on the whole dataset, we cannot get meaningful predictions. But we do expect that somewhere there should be a combination of variables giving rise to a good model. Well, then genetic algorithms is a good way to search for those variables. We cannot use, for example, model-based statistics, VIP scores, loadings, etc., because we don't have a model. But the genetic algorithm does not assume that we have a good model on all the data. It tries a lot of different combinations of data. The result of a genetic algorithm should not be seen as the solution, but rather as an indication of something that could be a good solution. That solution should probably be further refined manually, so to speak, by building models and modifying them. And that actually goes for all other variable selection methods as well. Let's try to use genetic algorithms. In the PLS toolbox, we have genetic algorithms by calling the function genalg. First, we will simply try to build a genetic algorithm without considering all the different settings. So simply open the graphical user interface, load the data, and run the model. and then we will see what comes out of it. You will have to wait a while until the iterations are stopped. If we look at the result of the genetic algorithm, we have a plot. The left plot shows the result from the last generation. Every circle gives the fitness cross-validated error of each individual model. To the right, we have the average and best fitting model as a function of generation. And we can see that the errors are generally decreasing with generations, which we do expect or hope, implying that we have selected variables that are better than we initially had. To the lower left, we can see the number of variables used on average per generation, and we can see that in this case it's been slightly decreasing throughout the generations. And finally, in the right plot, we see what variables were selected. In this case, it's very difficult to actually interpret the result. It doesn't seem to be very meaningful, and there's a good reason for that. And the reason is that we didn't modify the settings and the algorithm in such a way that it was suited for the data we had. And therefore, as a result of that, the results were not very good. We did improve the cross-validated errors somewhat, but we could have done much better if we had been setting up the genetic algorithm in a way that was more suitable. So we will pursue that. So let us try to see how we can generate more useful results with the genetic algorithm. First of all, it's an excellent idea if you can get an indication of the approximately correct complexity of the model. So meaning how many components you need. And then set the settings in the algorithm accordingly. Also, you may not want to use many iterations in your genetic algorithms because that will increase the risk of overfitting, especially if you have very few samples. Another way of avoiding that is to use multiple iterations of cross-validation. So every time you judge your result, or every time the genetic algorithm is judging results, it's based on many cross-validations. That is only meaningful if you can use random cross-validation. Otherwise, the result of multiple iterations would be the same. You can also run the genetic algorithm several times in order to get an idea about the variability in your results. If you have continuous data, such as spectral data, it is a very, very important thing to use a window. Instead of selecting individual variables, you will select windows of variables. If we look at the settings now, well, the population size, the higher the population size is, the more different combinations of variables we can try. And of course also the more we risk running into problems of overfitting. In general, the results are not too dependent on the population size though. The window width, the next setting, is very important. And you should set it sufficiently high if possible. If you have discrete variables, you don't use the window width, or you set it to 1. But for continuous data, have a as high window width as you judge being meaningful. The percentage of initial terms used is also, like population size, not the most critical one, but you may sometimes want to increase that in order to have more combinations of variables. There are also settings for having a target number of variables. This is not usually relevant, but in some applications you're interested in finding, for example, the 10 most significant variables rather than finding just the best subset of variables. And you can use all these settings in the lower left part of the user interface to set that. In the right part, you set the regression settings, whether you want to do PLS how you want to do cross-validation, etc. You can also read more about the settings in the PDF manual of PLS Toolbox. Now once you have your result with these improved settings, you should find that the variables selected are much more meaningful than they were before. It's a very good idea to repeat the genetic algorithm a few times and see how the results will vary, because they will vary because you start with different randomly selected populations. But hopefully with these better settings you should find a pattern in what variables are selected. For any specific model you may look at the results through the buttons in the user interface. Once the iterations are done, you can hit these buttons and look at plots reflecting how different variables are selected, how often they are selected, how often they are selected in the good and the bad models, etc. Overall, from running the genetic algorithm several times, you should get an idea about to what extent genetic algorithms can be useful. So you should notice that you do find good models in this case, and you should note that you never find exactly the same model. You just find a good model. Then you can take the result of that model back into the graphical user interface and do a PLS regression and refine the model further. Now we move on to the more classical methods and some of the more chemometric developments of these classical methods. In classical variable selection, which is typically based on having only a few variables, say 10 or 20, people often use statistical significance testing. For example, looking at the regression model, you get a set of regression coefficients. Now if you have few variables, you can use multiple linear regression, and there are well-derived expressions for the uncertainties of these regression coefficients. If you get a regression coefficient for a variable that has a certain value and then has an uncertainty that is high, so high that it actually cannot be properly assessed whether the regression coefficient is 0, well then you would try to remove that variable. That's the basic idea in significance testing. Then there are different ways of selecting sets of variables, such as forward selection, backward selection, and what is called best subset selection. If we start with significance testing, the idea is to do a regression model, and then you eliminate variables which are non-significant. That is, they are not significantly different from 0. That's a simple approach. It's very fast, but it assumes that you first of all have a valid model, a model that can predict, and that you have a way to calculate significance. Therefore, it's often difficult to use in more chemometric settings where you have very many variables and you have to use latent variables, PLS, PCR models. There is a function in the PLS toolbox that can calculate significance tests on spectral data, but the value of this is somewhat limited. There's another way to do significance testing though, which is more appropriate for highly multivariate data, and that's jackknifing. Jackknifing is based on cross-validation. When we do cross-validation, we take out one or several samples and build a model, take out another sample and build a model. So in the end, if we have 100 samples, we may have been computing 100 different models, but we only use the model calculated on the whole data set. We simply throw away all these different models that we have calculated, leaving out samples. But we could take a look at these models, for example the regression coefficients, and see how the regression coefficients vary when we leave out samples. And there's theory to calculate uncertainties of parameters. So we can calculate the uncertainty of the regression coefficients based on jackknifing, And that means we don't have to have a very strict statistical theory for the uncertainty of the individual regression coefficients. We can simply test it empirically through the cross-validation by using jackknifing. So the result is the same in the end, that we can select variables based on significance, but the significance that we get, the actual value, is different from the classical approach. And typically in the multivariate case, more relevant. Here's just an example showing a set of regression coefficients that have been calculated. And as you can see, variable number 4 has a low value, and furthermore, its uncertainty extends beyond 0. So we cannot say that this coefficient is statistically different from 0. Therefore, we should perhaps remove that variable. As you can see in this plot, there are many variables that are not statistically different from 0. And in practice, you may not want to remove all of them in one shot, because once you have removed a few of them, maybe some of the other ones behave differently. So in practice, you would usually select only a few of them and try to redo the model. So the idea in jackknifing is the following. You build a cross-validation, a PLS model using cross-validation, and then you of course have to check for outliers. Because if you have outliers in your data, well, then the whole result will typically be mostly influenced by the outliers more than the bulk of the data, and therefore you cannot trust the statistics that you get from them. But as soon as you are sure that you do not have any outliers, well, then you remove variables based on the jackknife estimated significance. And you do that repeatedly until you don't see any improvement in your model. Before we move on to forward selection, backward selection, we will discuss another variable selection approach that was developed some years ago, which is called iPLS, or interval PLS. The idea in interval PLS is very simple. It's mainly a tool that is useful for continuous data, such as spectral data. And the idea is that you build an overall PLS model, and after you build that, you build models based on only a small interval. So you divide your data into, say, 10 different intervals, and then you build a model in each of these intervals. And you look at the results that you get from the intervals compared to the overall model. Here is the result of using iPLS on the beer data. On the plot we see the average spectral profile, just to have an idea about where we are in the spectral range. And the red line, that's the error that we get if we do cross-validation on the whole dataset. Furthermore, we see the result of doing a local PLS model in each of the smaller intervals. And for example, around 1200 nanometers, we see that if we use variables within that range, we get much lower values than if we build calibration models based on the overall spectral profile. And for example, if we use only an interval in the visual area, we see that the error gets much worse than the overall model. This is a very visual idea, that you are able to look into what parts of the spectrum is important for prediction and what part is not. In itself, it may be of limited use, but it's good to provide an overview of your data, and it can be extended for selecting more than one window of variables, as we will show in the next slides. Forward selection. In forward selection of variables, we start out by selecting the best variable or the best window of variables, and then from that we try to find the next set of variables that, together with the firstly selected ones, provide the best results. And we continue for as long as we want to, or for as long as we improve the model. This is a nice approach. It often works well in practice. It's fairly fast, and it has the advantage that it doesn't require that we can make a good model on the whole data set. It doesn't use any information from the complete model, so it can handle situations with many irrelevant variables. Some argue that it disregards interactions, but in practice that turns out not to be a big issue, at least in most cases. Let's try to do forward selection on the beer data. In the beer data we have a lot of variables, 900, and there's a lot of redundancy in these variables. So it makes sense to use windows for selection rather than individual variables. The function iPLS can be used for variable selection. If you can do forward selection, well then probably you can also do backward selection. And indeed you can. And the principle here is that you start out from a full model and now you deselect variables. That is, you find the variable or the window of variables that improves the model the least. And then you deselect that part. And then you move on and remove next interval, until you get the best possible results. This sounds like a good principle, but in practice it often doesn't provide very clear results. First of all, you need to have a good model to start out with. Otherwise it's not possible to judge the effect of deselecting different variables. Also, the effect of deselecting variables initially is typically marginal, and therefore it becomes random which variables are deselected. So in practice this is often not as useful as forward selection or some of the other selection tools that we have investigated. You can also do best subset selection. We already discussed that a little bit in the introduction. The principle here is simply to try all combinations of variables. The good thing about that is that it's exhaustive. You check all combinations. The bad is that it's very expensive and it's simply impossible if you have many variables, more than 30 variables for example. And overfit is a real big issue here. So unless you have very many samples, it's highly likely that you can get misleading results from best subset selection. Now we have discussed a lot of different types of variable selection methods, and there are even more in the literature. What should be hopefully clear now is that none of them provides the truth, they all provide indications. And it's common to use several of these to get ideas about what variables are important, what variables are not important. If you are in a situation where you have many irrelevant variables, and by this is meant that you're not able to build a model on the raw data, then you should never use statistically based tests, jackknifing, significance tests, etc. And the fewer samples you have, the more important it is what kind of quality criterion you use. If you only have 3 samples and 8,000 variables, then using cross-validation is probably not going to work. So you have to have a strict quality measure if you have few samples. One way to get that, for example, is to use an independent test set or to do multiple cross-validations to make sure that the conclusions you draw are valid. Genetic algorithms, forward selection, those are the typical choices if you're not able to build a model on the whole data set. If you're able to build a model, that is, you want to refine a model that already works, well then you can start using the more statistically based methods such as significance testing, jackknifing, even backward selection. If you have continuous data, we already talked about that you should work in windows rather than working on the individual variables. If, for example, you have 900 spectral data, this is very complicated mathematically to explore. Whereas if, for example, you divide it into 50 windows, there's a much better chance of successfully finding a good set of variables. So therefore always work on windows if it's meaningful for the data. Another important aspect when you do variable selection is to remove outliers. It's especially important because many variable selection methods are based on statistical properties of the model, and these can be completely misleading when you have outliers in your data. And therefore it's always a good idea to remove a lot of outliers, possibly many more than you would remove in a final model, just to make sure that whatever conclusion you draw from the variable selection is based on a sound model, also statistically sound. There is an alternative to removing the outliers manually, and that is to use robust methods. But in practice, it's mostly more useful to look into the model and remove the outliers. So finally, with this course you should have gained some insight on how you can do variable selection under various conditions, and you should also realize that these methods do not provide the solution, but a solution that can be evaluated further by looking into the model. And also that the better the initial model is, the better results you can expect from variable selection. And having many samples, having few outliers, and getting rid of obviously irrelevant variables are some of the clues to getting a good result from variable selection.